As a scientist, I love questions. The more, the better. When I play a question game with my kids, extra points are awarded if the questions are tricky, and a special bonus is given if the questions are about something entirely familiar, but with very deep consequences. In fact, I almost always lose the competition, as I find that young children have some of the very best questions. Let me give you some idea of the kinds of questions I mean. Why is it that I can wave my hand through the air, but if I try to put one hand through the other, I clap? How can it possibly be that steam, water, and ice are actually the same thing? They seem to have totally different properties. Just what is fire? And what makes it glow? Essentially, the questions can all be boiled down to what are the ultimate building blocks of reality and what are the rules that govern them? Questions like these have perplexed humanity for as long as we've kept records. And, of course, with questions have come answers, with varying degrees of sensibility, from the four elements of fire, water, air, and earth, to the more modern ideas of chemistry. However, in the last 50 years or so, we have made some very rapid progress. Indeed, our modern understanding of the underpinnings of the universe can explain phenomena from the behavior of atoms to how stars burn. We have a name for this understanding. It is called the Standard Model of Particle Physics, or just the Standard Model for short. To understand what goes into the Standard Model, we need to recall some ideas we might have learned from school. If you've ever taken a chemistry class, you've heard that all of the matter of the universe is made of about 100 elements. However, even if you've never studied chemistry, you've probably heard that all matter is made of atoms. You've even probably seen this little logo for an atom, which shows a tiny nucleus with electrons swirling around it. Atoms like these are the smallest examples of the various elements, and you could reasonably think of them as the universe's ultimate building blocks. However, nearly a century ago, physicists realized that this wasn't the final word. We discovered that the nucleus of the atom was made of varying numbers of two particles called protons and neutrons. This was a substantial simplification in our understanding of the universe. Rather than 100 chemical elements, we now realized that with a mere 3 subatomic particles called protons, neutrons, and electrons, we could, in principle at least, construct an entire cosmos. And that is a pretty impressive achievement. However, during the 1940s through the 1960s, physicists discovered many more subatomic particles in experiments using particle accelerators. Rather than the simple model of 3 particles, literally hundreds of subatomic particles were discovered. Clearly, another simplifying insight was in order. The mid-1960s was when our modern understanding of the subatomic realm began to develop. Physicists realized that the familiar proton and neutron were made of smaller objects still. These smaller objects are called quarks. We now know of 6 types of quarks. They have kind of silly names, which are up, down, charm, strange, and top and bottom. Up and down quarks are found inside the proton and neutron, while the others are necessary to explain the vast number of discoveries made in particle accelerators. In addition to the quarks, there's another class of subatomic particles called leptons. The most familiar lepton is the electron, although it turns out that there are 6 leptons as well. 3 of these leptons have electrical charge. These are the electron, the muon, and the tau. The other 3 are neutrinos, which are electrically neutral. These quarks and leptons include every particle that we know of. The up and down quarks and the electron are the building blocks of the cosmos, and the other 9 particles have all been observed in our accelerators. However, while the building blocks of nature are important, we've forgotten an important point. This important point is force. Without forces, these particles would wander around the cosmos, not interacting with each other, and that would be bad. If something didn't stick the quarks and leptons together, there'd be no atoms, and consequently, no us. Physicists know of 4 different forces. The most familiar force is gravity. It keeps us firmly attached to the Earth and governs the path of the stars and the planets in the sky. It turns out that gravity is actually a very weak force, and we don't understand how it works in the quantum realm. However, the 3 other forces are very well understood. The next most familiar force is electromagnetism. Electromagnetism is responsible for electricity and magnetism, of course, but it is the reason why light exists, and in the context of building matter, its most important attribute is that it is the force that binds the electrons to atomic nuclei and makes atoms. The electromagnetic force is responsible for all of chemistry. The other 2 forces are less familiar. The first is the strong nuclear force, and it is this force that ties quarks together inside protons and neutrons and other particles physicists have discovered. The weak force is responsible for some types of radioactivity, and it plays a role in how the sun burns. These four forces have very different properties. Gravity and electromagnetism have a very long range, like the gravity from the sun affecting the path of distant Pluto. In contrast, the weak and strong nuclear forces only have an appreciable effect over distances smaller than the size of a proton. At distance bigger than an atom, these nuclear forces essentially don't exist. This is kind of like Velcro, where if two pieces of Velcro are touching, they're strongly tied together, but when they're pulled apart, they feel no force at all. The strength of the forces is really quite different. If we call the strength of the strong force to be 1 unit of strength, like 1 mile or 1 hour, then the strength of the electromagnetic force is about 100 times smaller. The strength of the weak force is about 100,000 times smaller. And the strength of the puny force of gravity between two particles is a 1 followed by 40 zeros smaller. This weakness of gravity is why we can't study it at particle accelerators, and it's a huge mystery. We don't understand why gravity is so much weaker than the other forces. Gravity is currently not part of the Standard Model. How do these forces work? In the realm of the super small, we need to have a different way of thinking about forces. At the quantum scale, forces are caused by exchanging particles. To understand how this works, imagine standing in a boat and having someone throw you a heavy sack. Your boat would move as if it felt a force. Similarly, if you throw a heavy sack off the boat would move. All the subatomic forces work by exchanging a different kind of particle. The particles are the gluon for the strong nuclear force, the photon for the electromagnetic force, and the W and Z bosons for the weak nuclear force. Physicists speculate about a particle called the graviton for gravity, but this has not been demonstrated. So that's the Standard Model. 12 particles of matter governed by 3 forces that are caused by the exchange of 4 particles. From these building blocks, with the right recipe, we can build the universe. Experiments with particle accelerators have completed our understanding of the Standard Model with amazing precision. Now, I don't want to leave you with the idea that there are no mysteries left to solve. While the Standard Model is the most successful theory ever devised, there are still frontiers to explore. For instance, the Standard Model includes a particle called the Higgs boson, which is thought to give mass to the other particles. We still have a lot to learn about the origins of mass. Further, we don't understand why there are 12 matter particles and why the quarks and the leptons are different. We don't know why there are 4 forces and where gravity fits into the picture. There are plenty of mysteries to solve. These are great questions, just like the ones we started the video with. It's an awful lot of fun to think about them, and there's no reason why we scientists should have all the fun. So I invite you to join my colleagues and I by reading up on these ideas. You could become a subatomic adventurer like us, exploring the quantum frontier.
Right, let's try that again.